Namaste and welcome back to this lecture on mathematical foundations for machine learning. We have been looking at lot many things in the last couple of classes. We looked at central limit theorem, we looked at sample geometry, we tried to compute the various statistics associated with the sample, where we looked at sample mean as a projection and then sample standard deviation as the length of the deviation vector and so on. Now, what we are going to do is in this lecture we are going to specifically spend time on covariance matrix, because covariance matrix forms what you call you encounter covariance matrices in almost everywhere in your machine learning. So, we are going to look at the how do we generate the covariance matrix, how do we get the covariance matrix, and we are going to look at what are the properties of covariance matrix. If you recall, when I was doing the real symmetric matrices, I said we will have to wait for some more time till I do covariance matrix, we will look at some important properties. So, that is what we are going to do right now. In this lecture we will discuss the covariance matrix. So, we are going to look at variance covariance matrices or the covariance matrices. So, I will call this as both are interchangeably used, variance covariance matrix or just covariance matrix. That is what we are going to see in this particular lecture. Okay, great. So, the first thing that we want to do is we want to define a few terms here. We want to look at what we call as a random vector. We will look at the random vector, idea of random vector, and then what we will do is we will look at getting to the covariance and variance covariance matrix as such. So, what we want to do is suppose I have a random vector, suppose x is a random vector, right. So, suppose x is a random vector, then so what do we mean by a random vector? We are going to say that okay, it is going to be a set of random variables, like okay. So, we are going to have this. So, we are going to say that look, you have an n by 1 random vector, that means you have an n component vector where each component is going to be a random variable. So, that is what we are going to call it as a random vector. We said that a 2 component vector where you take random variables x and y, and that is going to be a random 2 component vector. Now, we are going to do an n component vector where we have every component going to be a random variable here. So, what I want to do is I want to just straight away get into the idea of expected value of a random vector. So, what is meant by expected value of random vector? So, we have suppose x1, x2, etc., xn are random variables, we define x as the random vector, we define x the random vector as x is equal to x1, x2, etc., xn. Put all those n variables in a column format, you get the random vector x. Now, what I can do is I can actually find out the expected value of this x vector. What is that? It is basically the expected value of x1, expected value of x2, expected value of xn, put that in a vector format. So, what I am going to have is I am going to look at expected value of the random vector x is nothing but the vector of expected values e of x1, e of x2 and so on, e of xn, right. We are going to say e of x1, e of x2, etc., e of xn. So, basically what we say is the expected value of a vector, random vector, is equal to the a vector of expected value. So, that is what this means, right. So, this is what it is. Now, if this is the case, then I can do a whole lot of stuff. I can look at a lot of interesting stuff here. Before we get into the idea of covariance matrix, let's look at something interesting here. Now, okay, so let's first of all look at expected value of, let's say, suppose I have this vector. Let's do this. Suppose A is any vector, n component vector. A is equal to, let's say, A1, A2, etc., An. Now, what I want to figure out is, I want to figure out what is the expected value of A transpose the random vector x, right, A transpose x. So, basically I will take it this way, A transpose x. Now, what does this mean? This is nothing but expected value of A1 x1 plus etc. plus An xn. This is what we get, xn. These are all random variables. So, now what we have is, therefore, I have A1 expected value of x1 plus etc. plus An expected value of xn, because An are just scalars. So, what I am going to do is, I am going to remove all those An's out of my expected value operator. So, what I am going to do is, I am going to have this as A1 into expected value of x1 and so on, which is nothing but, again, I will write this as A transpose into expected value of x, A transpose into expected value of x. That is what we have. Just a minute. A transpose expected value of x. So, expected value of A transpose x is nothing but A transpose E of x, right, where E of x is going to be a random vector, right. This is what we have. Now, what we are more worried about, or what we want to look at, is basically variance. Let us look at let us say two random variables x1 and x2. I want to look at what is variance of x1 plus x2. And when we say variance of x1 plus x2, we already know that basically this is basically sum of two random variables. So, we know that the variance of the sum of random variables is nothing but sum of random variances plus 2 times covariance of these two guys. Right. Now, what I am going to do is, I want to find out variance of sum of n random variables. So, let me look at that. So, what we have, I want to look at variance of sum of n independent n random variables. So, I will not say independent, I will say I is equal to 1 to n, variance of sum of n random variables, which we already know. This is nothing but expected value of, you have sigma xi, the ith random variable, minus expected value of this, the whole square. We already know this, where this is going to be expected value of x minus E of x the whole square. That is what we have, and that is exactly what we have written here, right. Okay. So, what are we going to do here? So, we are going to extend this. So, what are we going to do? We are going to have this as, okay, let me just do this, let me just do a small substitution here. Let xi minus E of xi, I will say E xi, so that it says that expected value of the xi random variable. So, I will say, I will write this as E xi of xi. Let me call this as, say, some ui, right. So, what am I going to have? I am going to have variance of sum of random variables I is equal to 1 to n, xi is basically nothing but expected value of the random vector x of, what do I have here? I have put xi minus E of xi to be equal to u. So, I am just going to have sigma ui the whole square. And if you see this, I can write this as okay, I is equal to 1 to n. I will write this as expected value of, I will say instead of ui squared, and I will also get this, say for example we have expected value of a1 plus a1 plus a2 the whole square is nothing but a squared plus a2 a1 squared plus a2 squared plus 2 a1 a2. I want to accommodate for that. So, what I will do is I will just put a double summation here where I will say this is equal to I is equal to 1 to n and j is equal to 1 to n. I will write this as ui into uj. The square I can write it this way. So, what would this become? This is nothing but double summation expected value of ui uj, right. What is ui? ui is nothing but xi minus ex of xi and uj is nothing but xj minus ex of xj. So, this is going to be, so I will write this as I is equal to 1 to n, I is equal to 1 to n, this is equal to expected value of x minus e x I of x I into x j minus e x j of x j, right. So, I can write this as e x I x j, you get into the joint distribution function e x I x j of let us say x I minus e x I of x I into x j minus e x j of x j, and that is going to be what? This is expected value of x minus x bar into y minus y bar, which is nothing but my covariance of x I x j. So, this is going to be covariance of x I comma x j. Therefore, what are we going to have? We are going to say variance of this implies, therefore, I am going to have variance of sum of n random variables is nothing but the sum of all covariances. I is equal to 1 to n, j is equal to 1 to n, covariance of x I comma x j. We will just take a simple example which we will be able to understand better. So, we will just consider this, consider two random variables. So, what we can have? I am going to look at variance of x1 plus x2. Variance of x1 plus x2, I can write this as sigma I is equal to 1 to 2, sigma j is equal to 1 to 2, covariance of x I comma x j, right. If I put 1 to 2, so I will get this. So, what does this mean? This is nothing but just fix 1. So, I am going to get covariance of x1 comma j is equal to 1 x1 plus covariance of x1 comma x2 plus covariance of x2 comma x1 plus covariance of x2 comma x2. Oh, that is exactly what the expression that we want. That is nothing but variance of x1 plus 2 times covariance of x1 x2 plus variance of x2. This is exactly what we were looking for, and that is the expression that we have. Now, what am I going to do is I am just going to do a little exercise here, and I want to define a new matrix here. I am going to define in this 2 by 2 case, I am going to define a new matrix. So, what I am going to do is let us do this. Let Cx be a 2 by 2 matrix, or let be we define, okay. We define a 2 by 2 matrix Cx, which is given by this variance of x1, covariance of x1 x2, covariance of x1 x2, variance of x2. right, we have this. Then I am going to do something here, then variance of x 1 plus x 2, I can write this as 1 1 into my variance of x 1, covariance of x 1 x 2, covariance of x 1 x 2, variance of x 2 into this vector 1 1, which means I can write this as 1 transpose C x 1, right, 1 transpose C x into 1, where 1 is basically the 2 component 1 vector that I have, right. Now what we do is we are going to give a name for this matrix C x, we are going to give a new name for this guy. This guy is basically called the variance covariance matrix, variance covariance matrix. What is the how does the variance covariance matrix look like? This implies this has with variances along the diagonal, and covariances of along the off diagonal or the off diagonal elements. Now we see very clearly something from here. What is that? Variance of x 1, variance of x 2 are along the diagonal elements, the off diagonal elements are the same, covariance of x 1 x 2 and covariance of x 1 x 2. So straight away we find a very interesting property of this matrix, covariance matrix. What is that? The covariance matrix is a real symmetric matrix. Now all the properties that we have had of real symmetric matrix, we can completely dump it on the variance covariance matrix, right. Okay. So if you have n dimensional, you have let us say n variables. So let us do this. So in general our covariance matrix is basically something like this, it will look like this. You have variance of x 1, variance of x 2, etc., variance of x n. You have covariance of x 1 x 2, covariance of x 1 x 2, covariance of x 1 x n. You have covariance of x 1 x n, covariance of x 2 x n, etc., and so on. So we have this is going to be the variance covariance matrix. Now you can actually in fact you can, if you want to remove this variance term, then put it as a complete covariance, you can say covariance of x 1 comma x 1 and so on, that is still fine, right. Okay. Now let us look at some of the important properties of this covariance matrix. So some important properties of covariance matrices. The first important property that we have noted was C x transpose is equal to C x. That means covariance matrix is symmetric. How is it so, or why does that happen? Because you know that covariance of x 1 comma x 2 is the same as covariance of x 2 comma x 1. So covariance matrix is symmetric. Now let us take a very interesting idea here. Okay. So what we are going to do is I am going to look at this. Let us look at variance of let us say a1 x1 plus a2 x2. Now what is this? First of all, before answering what is this, you are looking at variance of some quantity, some random variable, let us say a1 x1 plus a2 x2 is equal to z, and that is the variance. And what is one important property of variance? This variance is always greater than or equal to 0, this is always greater than or equal to 0, right. Now what does this mean? Let us actually expand this variance that we had, variance of a1 x1 plus a2 x2. What are we going to get? I am going to get the following, I am going to get a1 squared variance of x1 plus a2 squared variance of x2 plus 2 times a1 a2 covariance of x1 x2. This is what I have. And what is interesting here, this quantity which is basically the variance of a1 x1 plus a2 x2 is always greater than or equal to 0, right. It is always greater than or equal to 0, in the sense the variance can never be negative. So this is basically always greater than or equal to 0. Now what do we mean by that? In terms of matrix, what do we get? We basically look at this as, I mean when you looked at variance of x1 plus x2, it was variance of 1 x1 plus 1 x2. So we wrote this as 1 1, we wrote this, if you look at here the coefficients were 1 and 1. So we wrote this as 1 1 variance of this, and then the covariance matrix, and then the 1 1 vector. So now what I have is basically a1 a2. So I am going to write this as variance of a1 x1 plus a2 x2, which is nothing but, I will write this as a1 a2, there we had 1 1, here we have a1 a2, and then I am going to have this as variance of x1, variance of x2, covariance of x1 x2, covariance of x1 x2 into a1 a2, this is what I have. Now this quantity, again I reiterate, it is always greater than or equal to 0 because it is variance stuff. Whatever value of a1 and a2 that you put, this will always be greater than or equal to 0. Remember we did this real, from the context of real symmetric matrix we did this. What did we do there? We said this matrix Cx that we had, you have this to be the A transpose A, this is the vector A and that is A transpose. A transpose Cx A is basically the variance of a1 x1 plus a2 x2, right. This is always greater than or equal to 0 for any value or for all values of a1 a2, the vector, any vector that you take in 2D. What do we call such matrix Cx for which you have A transpose Cx A is always greater than or equal to 0? Yes, that is interesting. We call such matrix Cx as positive semi-definite matrices, positive semi-definite quadratic forms we did. If you recollect the idea of quadratic forms, we did this A transpose Cx A, we look at Cx, therefore Cx is basically a positive semi-definite matrix. So we are going to say that the covariance matrix is positive semi-definite. Now what does that mean? Covariance matrix, so we are going to say Cx is positive semi-definite. Now what do we mean? Remember this positive semi-definiteness or negative semi-definiteness or positive definiteness or negative definiteness had a relation with eigenvalues of the matrix, right. When all the eigenvalues of the matrix is greater than 0, we called that real symmetric matrix as positive definite. when the eigenvalues of the matrix A, real symmetric matrix A is greater than or equal to 0, when the eigenvalues are greater than or equal to 0, we call such matrices as positive semi definite matrices. If you have matrices, real symmetric matrices for which the eigenvalues are all negative, then you call that matrix to be negative definite matrix. When you had the eigenvalues of a real symmetric matrix to be 0 or negative, you call that matrix as negative semi definite matrices, and the set of the matrices, real symmetric matrices for which you have eigenvalues to be both positive and negative, you just call them as indefinite. If you see here, for whatever values of A1 A2, the matrix CS you are going to have A transpose Cx into A to be greater than or equal to 0, which means I can go and talk about my eigenvalues. My eigenvalues are always positive or 0. Is that clear? So, that is the understanding that we have here. So, all the eigenvalues here, all the eigenvalues of this positive semi definite matrix or the covariance matrix are either 0 or I mean they are 0 or positive, right. Okay. Now, let us look at one more property. What is that? Let us recall, let us basically look at our okay. So, second property is Cx is positive semi definite. The third property that we are going to look at is the following. Look at the Cx matrix, the covariance matrix is basically variance of x1, variance of x2 and across the diagonal, I mean off diagonal elements are covariance fellows. Now, remember when we did covariance, we said that if the covariance is 0, then the random variables are uncorrelated, and we also said look, independent random variables will have covariance 0. In this case, suppose if the off diagonal elements are 0, then what are we going to get? We are going to get the covariance matrix of uncorrelated random variables. Is that clear? So, what are we going to say? We are going to say that if, so we are going to say that Cx for uncorrelated matrix random variables, uncorrelated random variables is a diagonal matrix and you pretty much know that the variance, covariance, everything that you have, these are all real values. Therefore, we typically say that covariance matrices are real symmetric matrices. So, we have of course that symmetry takes care of it, otherwise you will have to look at conjugate symmetry and stuff. So, what we have is we say that the covariance matrix is real symmetric matrix, right. One more important property, what is that? Okay, let us look at this. The fourth property. Suppose I have this, I do a linear transformation of the random vector x. Suppose I have this, let x be a random vector and we have y to be equal to Ax, right. I have y to be equal to Ax. That means I am trying to do a linear transformation of the random vector x to get the value y. Now, what I want to do is, and let us say and A is m by n, A is m by n, and we will also say that with m less than or equal to n. Okay. So, what is the covariance of the covariance matrix of y? So, we want to find out the covariance matrix of y. So, what is covariance, what is Cy? So, the question is what is Cy, the covariance matrix of y. Let us see what happens. So, how do we get the covariance matrix of y? Covariance matrix of y is nothing but we have this expected value of y minus expected value of y into y minus expected value of y the whole transpose. If we substitute all those values for y as Ax, what we get? We get y is equal to Ax minus expected value of Ax into Ax minus expected value of Ax the whole transpose. This is what we have. Now, what is that? Again I can do this, I can write this as expected value of, I have Ax here and then expected value of Ax is nothing but A times expected value of x. So, I will write this as A into x minus E of x, and I have this which is nothing but Ax minus E of Ax the whole transpose. I will write this as, so what do we get? We get here as x minus E of x the whole transpose into A transpose. This is what we get, alright. X transpose A transpose, this will become X transpose A transpose, this guy is going to become X transpose A transpose, X transpose A transpose, and this guy is going to become expected value of X transpose, and then you get your A transpose on the other side. So, what we have is this, and what is that? I can pull A out of this expectation. So, I get A expected value of x minus E of x into x minus E of x the whole transpose. I will pull that A transpose out. So, what do we have? We have Cy, the covariance matrix of the transformed random variable, which is basically y is nothing but A covariance matrix of x into A transpose. This is a very important understanding. So, this is property number 4. The next one that we have is another important property, property number 5. Remember, we said that when the covariance values are all 0, we actually get a diagonal matrix, and that just contains the variances. Basically, this diagonal matrix is nothing but the matrix, the covariance matrix of decorrelated random variables, right. So, what we are going to do is we are going to say that covariance matrix is always diagonalizable that means when you say diagonalizable, I am going to get a matrix which is diagonal matrix from this covariance matrix using, I mean we already know, like we can actually do an eigen decomposition and then get this. That means a matrix, a covariance matrix wherein which you have non-zero covariance values between random variables, you can convert that, you can transform that to, or you can diagonalize that matrix. That means you are essentially trying to decorrelate the random variables, and it says the covariance matrix is always diagonalizable, saying that, I mean you can always decorrelate the random variables, right. So, that is what it is. So, you can use your eigenvalues, eigenvectors, or you can even choose your A matrix. We just saw that, like Cy is equal to what is that, A into Cx A transpose. So, you can choose a matrix in such a way that you get a diagonal matrix, and typically you have multiple ways of doing this, right. The matrix A is not going to be unique. One way that you can do is you can use your eigenvalues, eigenvectors. So, I can find the eigenvalues and eigenvectors of this covariance matrix. I can diagonalize using the eigenvalues and eigenvectors and so on, right. Okay. So, when you try to get the, we just saw the matrices positive semi definite, which means eigenvalues, and you can also get the eigen vectors. So, what we do is like you can do the diagonalization. So, the diagonal matrix that you get, or the matrix with eigen vectors that you have, there is a name for that matrix with which you have this eigen, in which you populate the eigen vectors. You basically call that as the modal matrix, and that matrix is always invertible. So, we have you remember when we did diagonalization, we said A u is equal to lambda u, okay, a lambda 1 u, and then A v is equal to lambda 2 v, we said, and then we said A into u v is equal to, we had this lambda 1 lambda 2 into u v, sorry, we had this u v into lambda 1 lambda 2, this is what we had, right. Oh, basically these were the eigenvectors of the matrix A. So, we had A p is equal to P d, this is what we had, and this diagonal matrix, in case of the, you can do it in terms of the covariance matrix also. I can write this as C x into, let us say, some V matrix V is equal to V matrix into, let us say, diagonal matrix lambda, right. We can put this. So, what we have is we have V inverse C x V is equal to the lambda matrix which is diagonal, right. These are basically, this will contain your variance as well. So, you basically you get a diagonal matrix here. That means we say that the matrix C x, the covariance matrix, is always a diagonalizable. That is exactly what we are going to do, and you can always, I mean, you can suppose you get real symmetric matrix, C x is real symmetric matrix with distinct eigenvalues. Life is even more simple, because you get the covariance matrix to be diagonalized by orthogonal eigenvectors or orthonormal eigenvectors. That means you get orthogonal matrices which would diagonalize this covariance matrix, which means you will end up getting decorrelated random variables, right. So, this matrix V, which contains the eigenvalues, there is a name for this, we call this as the modal matrix, and V is invertible, right. So, we end up getting this, okay. Okay. So, pretty much we are done with this module of looking at inequalities. We looked at the sample geometry, we also looked at central limit theorem, and we paid extensive attention to the covariance matrix, because covariance matrix is something which you will frequently come across in machine learning. So, we looked at the properties of the variance covariance matrix, we looked at we said that look, these are symmetric matrices which are diagonalizable and which are positive semi definite, and we also looked at the covariance matrix of transformed random variable and so on. So, on that note, what we do is we have actually come to the end of the 4 weeks of probability topics. We studied various ideas in probability. We looked at we began with the basics of probability, where we defined events and all those things, and then went on till Bayes theorem. Then we started looking at random variables as something which will be helping you associate a reward. Then we looked at the different kind of random variables, continuous and discrete random variables, how we characterize these guys with, say, probability density function and probability mass function respectively. Then we looked at cumulative distribution function. Then we said that if nothing is available, we can always look at the moments of the random variable and discuss them. Then we said that look, it is not just this, suppose if two random random variables are there, we wanted to capture the joint behavior. We looked at the joint probability distribution, density function and so on, and then we also looked at joint moments. And once we did all that, we also looked at a bit of conditional probability, because the moment you say there are two random variables existing together, I want to find out, given all these features, like does this belong to that other class or so on. So, we were looking at that kind of a stuff, And then once we finished conditional probability, we said we will start with inequalities, where we looked at Markov-Chebyshev inequalities, which is independent of the underlying distribution for the random variable. We were able to get an estimate for the probability of finding the random variable beyond certain threshold, and especially in case of Chebyshev inequality, we were able to find out what is the probability of finding a random variable beyond some, say, n standard deviations, and we found that it is less than or equal to 1 by n square. That means the far you go away from your mean, then the probability is going to be extremely small, which is quite natural. I mean, which is very what we would say, which is something which we know, like from your CDF and stuff. So we understand this, right. And then we looked at central limit theorem, and then we looked at we brought the geometric idea to a sample. We looked at certain interesting things with the sample geometry. We were looking at sample as a vector, and then we looked at vector length to be something, deviation vector we figured out. We projected this sample vector on the direction of the vector which contained all the components to be 1, and we called that to be the mean. And then we found the difference between the data vector and the mean vector. We call that as the deviation vector, whose length was actually proportional to the standard deviation. Then we did a dot product of two different vectors, and we said that corresponds to the covariance with the factor of length in the number of points, or n being it's proportional to the covariance, as what we said. And then we also interpreted the correlation coefficient, which we already saw when we did two random variables. We said that the correlation coefficient is a value between -1 and 1, and we said that, look, that corresponds to the angle between the two random vectors. That's also something we saw. And we paid exclusive attention on covariance matrices, now looking at the properties of covariance matrices, because you will very frequently see covariance matrices in your data science and machine learning. So with this we come to the end of this probability topics. In the next class we will begin with multivariate calculus, where I will be starting with foundations. I will look at Taylor series and derivatives and stuff, and then I will get on to the idea of gradient and Hessian, and we do the gradient descent algorithm, and then we will start looking at the various applications. We will also look at neural networks, we look at stochastic gradient, and then we will also look at perceptrons, and we look at some regression and all those things. All those regression support vector machines we have already done. So we will basically look at these topics as a follow up of the ideas of probability, I mean the multivariate calculus. Namaste.